Hello everyone. In this video, I'm super excited to talk about an emerging technology, which is an artificial neural network. I want to grab your attention on points like what is neuron? What is neural network? What are the different layers used? In what way these layers are connected together? What activates the neuron? And the role of mathematics in artificial neural network. Let's talk about human brain first. Human brain consists of neuron, which transmit and process the information. Many such neurons are arranged together to form a network. They transfer electrical impulses from one to other neuron dendrites, which is the outer structure of neuron, receives the information from synapse of other neuron along with carrying the information to nucleus of neuron, where the information is processed and passed to axon, which is the longer branch among the dendrites, the synapse, then passes the information to dendrites of second neuron. This is how the network exists inside the brain. The same type of network is used in artificial intelligence, where we use artificial neuron to create artificial neural network, that is ANN. Working of this neuron is similar to the neuron in our brain. This is a 5. It's unpleasantly written and is at an extremely low resolution of 28 by 28 pixels. But your brain has no trouble recognizing it as a 5. And I want you to take a moment to know how crazy it is that brains can do this so effortlessly. This, this, and this are also recognizable as 5s, even though the values of each pixel is very different from one image to the other. The particular light sensitive cells in your eye that are firing when you say this 5 are very different from the ones firing when you see this 5. But something in that smart visual cortex of yours resolves these as representing the same picture while at the same time recognizing other images as their own distinct pictures in mind. But if I told you to sit down and write for me a program that takes in a grid of 28 by 28 pixels like this and outputs a single number between 0 and 10 telling you what it thinks the digit it is, it will be very much difficult, right? But thanks to neural network who helps here. I want to show you what a neural network actually is and to help visualize what it's doing as a piece of math. This video is just about structure components of neural network, and the following one is going to tell about learning. What we are going to do is put together a neural network that can learn to recognize handwritten digits. This is a classic example for introducing the topic. There are many variants of neural networks. And in recent years, there's been a boom in research towards these variants. This video is kind of a necessary prerequisite for understanding any of the more powerful variants. And trust me, it still has plenty of complexity to wrap our minds around. But even in the simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons? And in what sense are they linked together? By the way, neuron is a thing that holds a number between 0 and 1. Let's consider an image of size 28 by 28 pixels, so that there will be 784 pixels. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. So all of these 784 neurons form up the first layer of our network. Some number that's between 0 and 1 represents how much the network thinks that a given input image corresponds with a given digit. There are a couple of layers in between called the hidden layers. I have selected two hidden layers, each one with 20 neurons as an arbitrary selection. We can experiment with a specific structure here. If we feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image. That pattern of activations causes some specific pattern in the next layer, which causes some patterns in the next layer, which finally gives some pattern in the output layer, and the brightest neuron of that output layer is the network's selection. To recognize digit, we divided together multiple sections. A 6 digit has a loop up down and a line on the left. An 8 digit also has two loops up, top and down, and so on. Each neuron in the second to last layer corresponds with one of these subsections that when you feed in an image with say a loop up top, like a 6 or an 8, there is some neuron whose activation becomes close to 1. First, recognize the various small edges that make it up similarly along line, like you see in the digits. And I don't mean the specific loop of pixels. This way, going from the third layer to the last one just requires learning which combination of subsections corresponds to which digits. How would you recognize these subsections or even learn what the right subsections should be? And I still haven't talked about how one layer influences the next. But stay with me on this one for a moment. Recognizing a loop can also break down into sub-problems. One reasonable way to do this would be to first recognize the various little edges that make it up similarly along line, like the kind you see in digits 1 or 5 or 6. Well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. Let's consider an example of recognizing the digit 4, in which finding the required essential edges, one vertical edge on top left connected to middle bottom edge, which is then connected to long vertical edge, would be our initial step. These edges can be determined at various layers, including multiple hidden layers, and then combining the edges at final layer by activating the corresponding neurons at various layers to detect the particular digit. You can now imagine how being able to detect edges and patterns like this would be really helpful for image recognition. I personally find this satisfying rather than just treating the network as an imaginary box. Because when the network doesn't perform the way you expect, if you have built up a little bit of a relationship with what those weights and biases actually mean, you can start experimenting with how to change the structure to improve or when the network does work. But not for the reasons you might expect. Digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. Each neuron in the second layer of the network corresponds with the various relevant small edges. It lights up all of the neurons associated with around 8 to 10 specific small edges, which then lights up the neurons linked with the top down loop and also vertical line. This is how the activations in one layer determine the activations in the next layer. Our aim is to generate a system that can combine pixels into edges or edges into patterns or patterns into particular digit. What parameters should the system have? The solution is to assign a weight to each connection between our neuron and the neurons from the first layer. These weights are nothing but the numbers. Then take all of those activations from the first layer and compute their weighted sum according to their weights. These weights are organized into grid in which green pixels are assigned to positive weights and red pixel to negative weights. We apply this weighted sum only to region where we want to predict an edge. Weighted sum can be any number, but activations should be in the range 0 to 1. So we need to convert weighted sum to range of 0 to 1 using some function. Common function used here is sigmoid function. Let's talk about sigmoid function. Generally, very negative inputs converted into close to 0 and very positive inputs ended up close to 1. Basically, it is a measure of how positive the relevant weighted sum is. But neuron is to be active when the sum is bigger than a particular value, say 20. That is, you want some bias for it to be inactive. Then subtract this bias value from weighted sum before applying to sigmoid function. Bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. This way, each neuron is going to connect to all 784 pixel neurons from the first layer, and each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add onto the weighted sum before squishing it with the sigmoid. With this hidden layer of 20 neurons, that's a total of 784 times 20 weights along with 20 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them, all said and done. This network has almost 15,500 total weights and biases. Let's talk about the mathematics. All of the activations from one layer into a column as a vector, then organize all of the weights as a matrix where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. Taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product. Here, linear algebra comes into the picture. Organize all those biases into a vector and adding the entire vector to the previous matrix vector product. Then apply a sigmoid function to this. In this way, we can communicate the full transition of activations from one layer to the next. We can think of each neuron as a function that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. The entire network is just a function, one that takes in 784 numbers as an input and throw out 10 numbers as an output. It involves 15,500 parameters in the forms of weights and biases that pick up on certain patterns, and which involves iterating multiple matrix vector products and the sigmoid function. And that's a lot to think about. So this is all about initial aspects of building artificial neural network.